only doubly excited determinants, it's called a double CI. Okay, so today we'll do the independent electron pair approximation, which is related to the CI, but it is considered to be a separate approximation to full CI. So you must be familiar with the term full CI after the last few lectures. So that means you take the Hartree-Fock determinant, then you replace turn by turn 1, 2, or 3 spin orbitals with the higher energy virtual orbitals, and you obtain a set of determinants which are called excited determinants. If you have replaced 1 spin orbital, it is a singly excited. If you have replaced 2, then doubly, etc. And you can replace up to all n orbitals to get a n-tuply excited determinant. Okay, and when you take all such possible determinants, it is a full CI. You can have various approximations to this, and you have done the double CI in detail, which means that you only take the excited determinants which are doubly excited, meaning 2 of the occupied spin orbitals have been replaced by virtual spin orbitals to generate doubly excited determinants. And you take a linear combination of these determinants, and the combining coefficients are obtained from an equation which is derived using the variational principle again. Okay. And an important new concept which was introduced is the intermediate normalization. Which means that the overlap of the Hartree-Fock determinant and this new, you can say, correlated determinant, whatever level that is, whether doubles or full CI or whatever, that is equal to 1. The normalization of the Hartree-Fock function, that remains, but instead of the correlated function being independently normalized, you have what is called intermediate normalization, which is the overlap of the Hartree-Fock with the correlated function is 1. Okay. And the correlation energy is simply defined as the difference of the expectation value of the correlated wave function and the Hartree-Fock energy. So, E correlation is defined as the is simply the difference. Fine. Now, what is it I want to say? Okay, and the expression for this in general for a CI function, so E correlation CI is simply a weighted sum of the contributions of the various excited determinants to the expectation value of the energy. And these are the unknowns which are obtained via the CI equation. And I guess the method of solution you were told is the iterative Davidson method. So in principle, the CI equation is a eigenvalue equation. So you could simply diagonalize a huge matrix and get all your energies, but that is too expensive to do. So some special algorithms have been developed which enable you to get selected roots, most commonly the lowest root, which is your ground state correlated function. I guess Professor Pal would have talked about that as well. Anyhow, that is not important. The thing is that the unknowns are the coefficients. And here there is a restricted sum over all pairs of orbitals. Okay. And if I remove the restriction on this, then I can add a factor of 1/4. And I have two independent summations now. So here AB are the occupied orbitals which are replaced by RS, which are the virtual orbitals. Now this is not a standard notation. I am still using this because this is in Szabo and Östlund, so it would help you when you refer to the book. The most common conventions now, or the current global convention. So when you read recent papers, you will see that everyone uses the same, that I, J, K, these are the occupied orbitals, and A, B, C, D are the virtual orbitals. Okay. This is just an aside. Here AB is occupied and RS is virtual, following the convention of Szabo and Östlund. Okay. Now, so why are singly excited determinants absent from this expansion? Because of Brillou's theorem, which you have done before, and triples are absent, triples, quadruples, etc. Because when you have a Hamiltonian in the middle, it can only change the occupancy of up to 2 orbitals, because you only have maximum of 2 body interaction in the Hamiltonian, which is the Coulomb interaction. So that is why you don't have triples and quadruples in the energy expression. However, since this is an exact expansion, of course, the equations to determine the coefficients will involve your singly excited, triply excited, all the excited determinants. Only the energy expression only has the doubles. Okay, so be careful. This is not just for double CI. This is for full CI. Okay. Now looking at this expression, since the energy expression at least only involves the pairs, if we ignore for a moment how we determine the coefficients, we can write the correlation energy as a sum of certain pair correlation energies. So what I have done, I have separated the A not equal to B summation and put the rest into a pair correlation energy EAB, where EAB is equal to R not equal to S CAB to RS psi 0 H psi AB RS. Okay. So is that clear? So this is just a definition of a pair correlation energy. Now if we knew what our coefficients are from a full CI solution, then the pair correlation energy is exact. Okay, so far we have not made an approximation. Now what is the approximation that we do to simplify our calculation? We say that we want to calculate the pair energy of each pair of electrons independent of the other pairs. So what is the approximation? So now we make the approximation. This is independent electron pair approximation. So what is the approximation? That you compute EAB independent of ERS, let's say. So how will we do this? So we again go back to the expansion of the wave function. So here I can tell you something. So the theories that we do in this advanced quantum chemistry course, they are all called wave function based methods. Okay. So wave function based correlation methods, what that means is you start out by approximating the wave function. You are not approximating the Hamiltonian. You take various physically motivated approximations for the wave function, and then you proceed to determine the variables that you introduce into the wave function. The other alternative is density functional methods, where you introduce approximations to the density, which is an integral over the wave function. So that is a less detailed quantity. So when you integrate something, the internal details or internal degrees of freedom get integrated out. So the density is a simpler quantity. The wave function is a more complicated quantity. It has more parameters and more variables. When you do wave function based methods, you take approximations on the wave function. When you do density functional approximations, you do take approximations on the density. The density functional actually involves approximations in other things, but you can never get back to the wave function from the density based method. So I just wanted to mention that, because here you will see we will always start any approximate theory that we do by writing an expression for the approximate wave function. So in CI you wrote it as a linear combination of various excited determinants, and here I will write the wave function for every pair of electron as a linear combination of pair functions. So the particular approximation here is that you can consider this AB as a single index. Okay, so you can consider them as a single variable. Okay, so what that means exactly is that I have n into n minus 1 by 2 variables to be obtained. So I have n into n minus 2 unique pairs of orbitals, and my variables in the wave function are pairwise. Okay, so we will never so in my coefficient CAB to RS, if this is 1, then C, let's say so CAB to RS is one variable, then CAB to RQ is another variable, but let's say so AB going to RS, but what I don't have is C RS to, let's say, RSTU. So this is not there. So such a variable is not there. So RS is, AB is an occupied orbit, are occupied orbitals, RS are virtual orbitals, and TU is also, T and U are also virtual orbitals. So a psi RS is a doubly excited determinant. A psi TU is a doubly excited determinant. It is possible to have to have a value for psi rs. So for
Hello, ma'am.
yeah,
Hello, C of D to ST possible. Hello.
to st, c of rs to st,
No, no, madam. C of CD to ST.
cd to st. So yeah, cd is occupied. Yes, this is possible. This is just another pair. So every pair is one unit, and you can replace, and every virtual pair is also another unit, and you can take one occupied pair to another virtual pair. Yes, this is possible. But rs to tu is not possible, although psi rs h psi tu is a valid quantity because they are doubly excited with respect to one another. So this is a valid quantity, but this will never uh, be required in my independent electron pair approximation. This is required for your double CI. So in the double CI matrix, you have the did Professor Pal use this notation like the P space and Q space? So you have the PP space here, the PQ here. Sorry, PP, PQ, yeah, PP, PQ, QP, QQ. So this QQ space means you have matrix elements between doubly excited determinants, which are doubly excited with respect to each other. So in double CI, you have this, have a role. So this plays a role, but in the independent electron pair approximation, this does not play a role. Okay, we will come back to this. It will become clearer when we do the derivation. Yeah, yeah. Ask.
What is the range of natural organisms? I mean, up to.
I can't hear you. Can you repeat once more?
What is the number of natural organisms? How to calculate that?
The
How
number
many?
of occupied orbitals is n.
Yes.
So n is
No, that's occupied.
number of virtual depends on what basis you have started out with. So number of basis functions minus number of occupied is number of virtual.
Okay. And you said that IJK are occupied orbitals or IJK are.
Yeah, no. This I just mentioned in case you refer to some recent paper or something at some point. So the currently accepted naming convention, that's just names, is that the IJK letters are used for occupied orbitals and ABCD are used for virtual orbitals. But in Zabu and Oslund, ABCD are occupied and RSTU are virtual. So I am continuing with the old Zabu Oslund convention. But for example, when I do coupled cluster, I will shift to the current conventions. So just a warning. Okay, so is that clear now? Yeah. Okay. Let me continue. So this is actually where you start the independent electron pair approximation, and then the energy of this. So this is okay. Oh, I'll just erase this. Okay. Solves the problem. Okay. Then the energy of this wave function, which is basically the expectation value of the independent electron pair wave function that we have taken, and that so you have psi 0 h psi 0, which is simply your Hartree-Fock energy, and the rest So look at the EAB. It's not scrolling. Why is it not scrolling? Okay. Yeah. So the cross terms, you have psi 0 H psi ABRS. If I project with psi 0 over here, so that will give me a EAB. Okay. Fine. So this is simply E0 plus EAB as we have defined it. And this is called the pair correlation energy. And you have n into n minus 1 by 2 of these terms. And my okay. Then let us look at the Schrodinger equation with this approximate wave function.
Madam,
Yeah.
ma'am, how REAP wave function is different from CI wave function? I mean, it's just the difference is like we are excluding the other excitation wave function in CI, singlet, triplet, and just taking the double excitation of CI.
Uh, okay. So in CI, you would replace. So you generate the. So let's say. So in CI, you have these doubly excited determinants, and then you take when you take the when you generate matrix elements between the correlated wave functions, you generate terms which are what is it called? So these terms, the ones which I wrote, that you have two excited determinants. So let's say AB to RS, H psi, AB to TU. So you have terms where you have projected this with where you have doubly excited. So both these wave functions are doubly excited. With respect to the ground wave function and also with respect to each other. So uh, this matrix element, let's say, or this quantity appears in the CI equation. But in the independent electron pair approximation, you would not consider this. So this term is actually a sort of coupling between the RS excited pair and the TU excited pair. But when you talk about the independent electron pair, then every occupied electron pair interacts independently with the virtuals. So there is no coupling between an AB pair and a between a RS pair and a TU pair. So the doubly excited determinants do not couple with each other. They only couple with the occupied pairs. So that is the difference. Maybe when we write the matrix equation for the IEPA, it will become clearer. Okay, just hold on for 2 minutes. I'll write it in, yeah, I'll write the equation in a few minutes. So like, for example, the Schrodinger wave equation here, we have simply written it for every pair, for each AB pair, independently. Okay, we have not written psi, we haven't put a sum here. In double CI, you would have put a sum here. or written it as H psi correlation double Ci is equal to E correlation double Ci psi double Ci. But here we have separated it out into every pair. Okay. And then you continue with this approximation for each for each occupied pair. So now I write psi AB as this function, that it's the Hartree-Fock determinant plus the doubly excited determinants. Okay, I'll write this as this is for a particular reason. A little bit later, you'll see why I wrote TU AB to EAB psi 0 sum t not equal to CAB TU psi AB to TU. Okay. Fine. Now this equation I project once with psi 0 and I get E0 from the first term plus sum t not equal to u CAB to TU psi 0 H psi AB to TU. Okay. And on the right, I don't have a Hamiltonian, so my intermediate normalization will come into play. So I have EAB, psi 0 is 1 and psi 0 psi AB to TU, that is, no, what happened? Is that 0? Yeah. So psi 0 and psi AB to TU, it is 0 by Slater's rules. So the overlap between a ground state determinant and a particular excited determinant is 0. The intermediate normalization holds for the entire wave function. Okay. But individual determinants, the overlap, it is 0 if they differ by even one spin orbital. So this is 0. And then I project now with the excited determinant. So where the AB pair has been excited to the RS pair, and there this is 0. Then the first term is 0. Then the second term is psi AB to RS H psi 0. Oh, sorry, I shouldn't have said that. So this first term gives me this. Now we have an H here, so it's not 0. And then we have T not equal to U psi AB to RS H psi AB to TU, okay, multiplied by CAB to TU. And on the right hand side, now this term psi AB to RS psi 0 is 0 and psi AB to RS psi AB to TU that is 1 only when RS is equal to TU. So when the RS composite index is equal to TU, which means that the RSth pair is equal to the multi-youth pair. So the RS composite index goes from 1 to whatever number of virtual function, n virtual into n virtual minus 1 by 2. And yeah, so when it is the same pair, then my second term on the right, that remains. So I get the right hand side of my equation. So this is equal to EAB psi AB to RS psi AB to RS. That is equal to EAB. Now I also know that this term so this was small EAB. Right? This was equal to small EAB. Isn't that so? So then I can scrolling. Okay.
Ma'am, CABRS term should be there with EAB, I think.
Yes, that is right. Thank you. Yeah, this should be there. That is right. Okay. And so knowing the definition of EAB, the small EAB, I can. So this is consistent with what we got as the energy expression before. Remember, we wrote E capital A, EAB as E0 plus small EAB. That is my energy expression then. And the second equation becomes psi AB to RS H psi 0 plus sum T not equal to U. So this I'm doing from this equation. So here also I can write EAB over here. So it's this psi AB to RS H minus E0 psi AB to TU into C AB to TU, and that is equal to small EAB CAB to RS. So I've just taken some terms to the left and right from equation 2. And this is my working equation then. To obtain the coefficients CAB, RS and CAB. So now this is my working equation to get the set of coefficients CAB to RS. Okay. And now we can recast this the energy equation and the equation for obtaining the coefficients as a matrix equation. So we combine the two equations and we define some quantities. So let's say I define this. So this quantity, or rather, wait, not the coefficients. The coefficients are my unknowns. So this is a known quantity, and I define each each element. So if I call this a matrix D, then the RS-TU element of the matrix D. So this is the matrix D and this is the RS, comma, TU element of matrix D. Okay. Using RS and TU. So note that here AB is a fixed quantity. So this is an equation for a given AB. Okay, all the CD and DE, whatever other pairs, they will be solved independent of the pair AB. And I have the RS-TU element of a matrix D then given by this expression. Then I have, let's call this. This is another matrix, let's say B, and this is the RS element. Okay. So this is actually a single index. I'll put some brackets here so that you don't get it. So this is a one number. RS is one number, and that is the RS element of matrix B. And this variable C, I can call it the RS element of matrix C. So these are matrices B, D, and C. So now if I write my matrix equation in this, the equivalent matrix equation of the two algebraic equations that I wrote, then I can write this as 0, B dagger, B, D, 1, C is equal to E, AB, 1, C. So the 1 corresponds to the energy equation. So if I just and the second row, the C part corresponds to the equation determining the coefficients, and this is for each AB. So you have a B matrix for every AB pair, a D matrix for every AB pair, and a C matrix for every AB pair. You could thus write an additional index on all these matrices and write them as AB, 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 okay, AB if you like. Okay. But this AB is not an index which enters the solution of the equation, if you understand what I mean. So you have an equation for every AB and you solve it independent of a CD index. So that is why this is called an independent electron pair approximation. So you have n into n minus 1 by 2 number of independent equations, and you obtain a set of values for small EAB. And then you compute an overall correlation energy at the IEPA level, which is a sum over all the unique AB pairs. You just sum small EAB. Okay? So is that clear? So it's a bit different from what you do in a CI. So in a CI, you would obtain E correlation CI by the solution of a single matrix equation. And that involves the coupling between all pairs of excitations. But here, the correlation of every pair of electrons is independent of the correlation of the other pair. And after you solve these separate equations, you just add the individual pair correlation energies to get a total correlation energy. Okay, so it's also called a pair at a time CI sometimes. So is it clear now how it is different from CI? Someone asked me a question.
Yes, ma'am.
Yeah. Okay. So that is basically the method. And as you can see, it is also then computationally relatively cheaper than a CI. Okay, and this is also the starting point for coupled cluster theory. The other aspect of this theory is that it has a cleaner connection to perturbation theory. So there are two different types of perturbation theories which you can arrive at from this independent pair approximation by using some mode approximation. Okay, so since we have about 10 more minutes, I can do that. So further approximations to get perturbative expressions. Now, the advantage of perturbative expressions is that it just involves evaluating an expression. A perturbation theory will not normally involve solving an equation. So that makes perturbation theories always cheaper. Okay, you get an expression for the energy or you get an expression for the perturbed wave function and you just evaluate it from known quantities. You don't need to solve something. Okay. And so how can we remove the requirement of solving something from this? So the first thing that people did was you remove the coupling between so we have over, let's see, where did that go? Yeah, you have a coupling between CAB-TU and CAB-RS. Okay. If we had TU equal to RS, then I would have an expression for CAB-RS and I wouldn't need to solve an equation. So that is what people did. And by people, I mean this was, I think, Epstein and Nesbet, or yeah, probably. Yeah, I think it was Epstein and Nesbet who did this approximation. So they said that let's see, how should I write it? That in the, let me label this equation. So equation 2, and I can say this is equation 1. So in equation 2, remove coupling of CAB-RS and CAB-TU. And then the expression that I get by putting T equal to R and U equal to S gives me psi ABRS H psi 0 plus psi ABRS H minus E0 psi ABRS into CABRS. So I've removed the sum over T and U. that is equal to EAB CAB RS. Then we solve this equation for CAB RS. Okay. So what is CAB RS then? CAB RS is simply psi ABRS H psi 0 by psi ABRS H minus B0 psi ABRS minus EAB. So now I only have an expression direct. I just need to evaluate this and I get my coefficients. And I replace the value of this coefficient now in my energy expression, and I straight away get an expression for the energy, the pair correlation energy, and that is sum R not equal to S. I will get mod psi 0 H psi ABRS squared by this entire thing. So psi ABRS H minus psi minus B. Okay. But see, there is a problem now. So this is not exactly an expression yet because I have EAB on both sides. So here you make the following consideration. So consider that EAB would be typically much smaller than the excitation energy between psi 0 and psi ABRS. Okay. So there are two terms in the denominator. You have this one. What is this? So this is the expectation value of H between a doubly excited determinant. So that is the energy of the doubly excited state. And then you have minus E0, which is the energy of the ground state. So this is basically the double excitation energy. This is basically a double excitation energy. Okay. And this is a correlation energy. Now, typically a correlation energy will be several orders of magnitude smaller than an excitation energy. Okay. So, making that, well, not an assumption, but the consideration of the reality, you can ignore EAB relative to the excitation energy. And now I get the final expression for my pair correlation energy, which is sum RS mod psi 0 H psi ABRS mod square by psi ABRS H minus B0 psi ABRS. Okay, and this is what is called the Epstein-Nesbet perturbation theory. Okay, and then the corresponding total correlation energy of the Epstein-Nesbet perturbation theory, that is sum A not equal to B small EAB EN. Okay. So that is the Epstein-Nesbet perturbation theory.
Ma'am,
Yeah.
ma'am, this EAB energy, does it represent like amount of total some amount of total correlation energy between the orbital A and B?
Yes. Yes. So it's the correlation energy for every pair. So here the physical idea uh, is that the probability of two electrons interacting between themselves is more important than three interacting together or four interacting together. So in a probabilistic picture, like if you even consider the collision picture, two body collisions are more likely, like far more likely than three or four body collisions. So from that point of view, they say that the pairwise correlation energies are the most important parts of the total correlation energy. So that's why these pair approximations work in a way. So it's a part of the total correlation energy. Yeah. Okay. So some further approximation you can make over here is on this quantity. So more approximation. So furthermore, I can approximate this excitation energy at the Hartree-Fock level. Okay. So if I do that, then so if you did not change the orbitals at any point of time, then the Hartree-Fock expression using only Hartree-Fock orbital energies, this can be approximated as simply the difference of the orbital energies. So you have removed electron from A and B and put them in R and S. So the difference in the orbital energies is the difference in the energy of the determinants, the ground state and doubly excited determinant. And when you use this expression, then you can get a further, more approximate pair correlation energy, and that is sum R not equal to S. So there is a minus sign here, which you can shift to the denominator, but let's not do that. So it's ER plus ES minus EA. So some people will shift this negative sign to the denominator and do EA plus EB minus ER minus E. That's also fine. Okay. And this is called the first order approximation to the Epstein Nesbet perturbation. So there are various levels of approximation. So that's it for the independent electron pair theory. So we will stop here for today. So next class is Wednesday, and this quiz on April 9th. Okay. Thank you.